All right. Can you hear me, everyone? All right. Let me see if you can. All right. Uh, all right. Perfect. Hi, everyone. Is are you able to type? Can you check if you're able to type? Hi, hi, Prabhu. All right. Okay. Okay. Perfect. Perfect. So today's session is going to be a little more technical, and it's going to be, much more. We will be diving deeper into the maths behind the XGBoost. Okay, so so before XGBoost, okay, let me give you a timeline. So previously people were doing the linear regression. Linear regression is something that was most common, and people did linear regression for training models. Then came SVM. SVM was able to do really, really, really good. And then though people were using the decision trees, but it got mainstream after random forests came into play. Okay. After random forest, basically at that point of time of random forest or SVM, the neural network were not really, really efficient or were not able to do the good job. So, and at that point of time, people thought that SVMs are better than neural networks, and then random forests are better than SVM. And then came XGBoost. XGBoost was XGBoost was I think was done by Tianqi Chen, one of the students who was doing the internship. And in internship he was essentially implementing the gradient boosted trees as well as the random forest. So he was implementing that library, and that's when he designed and came up with XGBoost algorithm. XGBoost has been very successful. since the time of inception till I think 2016 or so. I think 2016 or so. XGBoost was the most favorite algorithm for winning most of the Kaggle competitions. Okay. People won the Kaggle competitions with this XGBoost. But today, people don't use XGBoost that much. Okay. People use the neural networks, and most of the work basically has been overtaken by most of the neural networks, right? Now, XGBoost is still used for classic machine learning problems. And if you are not using, you don't have too much of data for neural network, you would still use XGBoost. Okay. And the important part to understand is that why are we conducting this webinar, right? When you are saying that this is not used much, or when I'm saying that it's basically something that was of the previous decade. The important part to know about XGBoost is that XGBoost is a clever, very, very clever algorithm. It is worth knowing XGBoost, right? So trees were simplistic, right? Trees were very simplistic, whereby you go over all the features, you try to split the data, and then you keep on, doing that. In case of XGBoost, in case of XGBoost, the idea was to basically um, do that very cleverly. Okay, do that very cleverly, and that's what we're going to do. So the purpose of this session today is to dive deeper into the algorithm, how exactly does it function. We did not find too many details on, or we did not find, the detailed videos on XGBoost. Therefore, we decided that we will have this session for everyone. Okay, the XGBoost in general, the XGBoost algorithm. If you go through the original paper, you'll find that XGBoost has got fair amount of maths to it. So and therefore, be aware that this session is going to be a bit more mathematical. But I'll make sure that we understand it. We understand it in a simple words, and then we basically are able to handle the maths. Okay. All right. Okay. So I think most of you know me, but those who are coming for the first time, okay, let me just have a quick check if it's streaming or not. Okay. And yeah, it seems to be streaming. All right. Yeah, it is streaming. All right. Perfect. Perfect to have all of you in this discussion. So this is myself, and right. So I graduated long, long back ago, 2002. And then I worked in large scale computing, then software engineering, machine learning at Amazon in Movie D Show. I even had it at DevRev for some time. And then I started, right. So not that like CloudX Lab, I started long back. And the and now we are starting with something called Turno. So Turno AI is essentially our, you know, like a data scientist on your relational data. So I'll mention that later. Now, so today we are going to basically go into much more details about the XGBoost. So feel free to ask questions whenever you have any doubt. Okay. So except for myself, everybody is on mute. And if you are on YouTube, please use the YouTube chat. If you are in the Zoom meeting, you please ask the questions on Zoom. Okay. All right. So, yes. Now, okay. With respect to CloudX Lab, CloudX Lab basically was, started from the perspective that the world needs technologists, and there's a gap in the industry. Okay. So we decided to build, started to teach people into deep technology, and that turned out to be extremely successful, right? One of the inventions that we did at CloudX Lab was a playground where people can, exercise and learn, and it gives you the feedback immediately. Okay. And it also gives you the direct access to most of the tools, and you're free to experiment with anything. It provides you the real world experience, seamless and centralized data sets, along with you can access with any from any devices. The social media, right? Like you can maintain your own social profile. We have a dedicated job portal, and we conduct something called placement eligibility test. You can sign up for the eligibility test, and then give the test. We connect you to the recruiters and so on. Now, the okay, so we have quite a few courses on AI, and these are probably the most detailed courses. And the live course that I run with the IIT Roorkee, those courses are designed to build inventors, right? So we go into details instead of asking you to memorize the algorithms or memorize the models. Our focus is that you derive them. Our focus is that you code them by yourself. And that's how the entire course is about. Entire course is about l- l- learning to invent. So you learn by inventing things. Okay. So we have been fairly successful um, in this approach. So this is one of its kind course. This specifically the first one. This is one of its kind course because in this course, essentially we go over like very fundamental things, and everybody has to design and build things. Now, this might sound very awkward, but the truth is that if you're going for a job or if you're applying anywhere, today, people won't ask you what is machine learning. People won't ask you what is disease entry. Instead, the question would be, how would you code this? How would you code the Gini impurity? How would you code linear regression? So that's the kind of question that people would ask you in the interview. And these questions will not be like a direct question. They'll be like a fairly indirect questions, and you might have to code most of the things. Okay. And you can only clear these interview rounds of today's, right? In last couple of years, this whole pattern had changed. Earlier, it was machine learning and AI used to be a theoretical interview, but now everything is very hands-on and coding oriented. Okay, for example, for a machine learning engineer, people might ask, like, can you solve these consecutive equations or write the code to do the consecutive equations? So, so make sure that you do the hands-on, and if you want to do it, with the full with a certain guidance, do come to my class. My classes are very much like a gym class. instead of consuming videos, you work out. Okay, so that's how the classes are. So you're welcome to my class. And yes, now the before we start with respect to the gradient boosted trees, I want to just do a little bit of the overview of the mathematical symbols. Okay, right? So here you see this X. When we say X, X means it's a training example. This is ith training example. And this R and D is your that Xi is an element. This E means that Xi is a part of this data set called R and D. This is a training data. Okay. So this means Xi is an instance, or you can say Xi is an example. It's an example row of the data, which is part of this data set, which contain many such rows. Okay. Now, basically, the main problem is only the annotation. So that's where you will zone out. So as long as you are comfortable, make yourself comfortable with symbols, everything else will become okay. All right. Now, basically, what exactly is a model when we say model, right? Model is something that gives the prediction given the input. So xi is the row of the data. We feed the data to a model, and model is supposed to make the prediction y. Okay, so basically the machine learning model learns from the data, and once it has learned from the data, when a new example comes in, it predicts the y. This is a supervised machine learning, so it has x and y, not only x. Okay, so we feed x, we get y, as simple as that, right? And what exactly is the linear model? Linear model is saying y equal to mx plus c, right? You remember this part, everybody? Okay, so, and let's see why I'm not able to draw. Okay, most likely I'll have to change my other account to organizer. Okay, okay, now, all right. So this may be a little more, complex when you look at it, but this is essentially y equal to wx plus, okay? This is what it means. The hat, usually you see this hat, it means that this is the predicted value, okay? So these W's are W's are basically, basically, the weights. So if you ignore the sigma for a moment, and we wanted to put it like this, okay? Raised like this. Okay. So W0 plus W1 X1 plus W2 X2 like that. Right? So if this is let's say we have an instance number one. So we are feeding the first column of the instance, second column of the instance, and third column of the instance. Okay. Here. Okay, so this sigma means summation over j, where j is going over all the columns of the data. So W0 times x something and so on. So this is usually 1. This is usually 1. So we are saying, just like we had y equal to mx plus c, this is the generalized version of the same. We are saying y equal to mx plus c. Okay, just that if you have many x1, x2, x3, we would write it like this. Okay, I hope everybody is okay with this. Yeah, please put it in your chat. All right. Okay. All right. Now, now the prediction score can have different interpretations based on the task. If it's a regression, then y is a number, right? If it's a classification, then you would like to predict the probability of an outcome, right? We give the number like a decimal number. And how do you convert any number into decimal? By making it pass through this one. Okay. So this is basically called logit, right? If you pass any number through this, it will convert it into probability. Like if y is a very small number, y is a very small number, what will happen? This thing will become very big and hence it will become zero. Correct? If y is a very big, y is a very big number, then this will become 0 and hence will become 1. So this will result in between 0 and 1. This will result in something between 0 and 1. So all we do is, in case of logistic regression, we convert any number by passing it through this function to something between 0 and 1. Okay, this is the basically, because let me step back. Okay. I hope my voice is clear. Okay. Right. So what usually happens is that we pass X into this big box where we multiply with the weights, all the input, and it gives the outcome. Right. Now, in case of the regression, it's okay. But in case of classification, what are we trying to do? We are trying to say that our model should say that whether it's yes or no, right? There's nothing in between, correct? So what do? We put one more filter or one more transformation here, okay? We call that logit, and this looks like 1 by 1 plus e to the power x, meaning if this thing is very big, it'll become 1 by 1 plus e to the power minus infinity. This will become 0, right? Sorry, if x is very big, it'll become 1 plus e to the power minus infinity, and hence it'll be 1. If x is small, right? Okay, if x is small, let's say e to the power, let's say minus infinity, right? So this will become very big number, e to the power infinity, and hence this will become 0. So when this value is right, so this basically, this outcome becomes something between 0 and 1. That's the whole purpose of putting this. So basically, this logistic function converts any number to between 0 and 1, and we can interpret it like a probability. Rest is all the multiplication of these numbers. Okay, so yes, I hope this is making sense, everyone. Are you guys okay? Perfect. Perfect. All right. So we talked about the machine learning model. Consider it like a recap of what we have learned earlier in the supervised, unsupervised. Okay. This essentially means we are multiplying some numbers to the input and adding some number to the input to get the outcome, right? And further, we are also doing this translation to convert the output into something between probabilities. So we will essentially, what do? We tweak these weights until our outcome starts matching with the expected outcome, correct? Right? So we basically tweak these weights until the outcome starts matching with the expected outcome. All right. So the things we need from the data, right? So usually we define something called objective function. Okay. So for every column of the data, we needed to find W. Okay. So here this is called the linear model. Same thing what we did study earlier. So linear model, theta is basically nothing but an array of numbers. Okay. Linear model is nothing but array of numbers. Okay. So when you have, let's say, a data like this is your data, and you fit the line. Okay. Your equation of the line is sum mx plus c, correct? Where m and c are basically the parameters. So here, this wi, and this is essentially saying this is m comma c. Okay. This means we have got theta is nothing but a bundle of weights that make up the model. And this pipe means here this vertical line. Usually you'll find in the papers that this line, okay? It means theta is wj, where j is between 1 to d. Okay, d is number of features. All right. So this essentially means it's an array of numbers where each number represents a weight. Just like m and c in case of straight line, if you have a plane, it'll be W1, W2, W0. In case of something else, it'll be more number of parameters. In case of ChatGPT, this will be a billion numbers. Okay. Now, what exactly is our objective function, right? So objective function is number one, a loss function. Okay. Like when we have like the data, right? We have these, let's say 3 data points, and we are trying to fit a straight line through this, right? So for this value, this much is the actual, and there is this much is the difference. For this value, this much is the difference. For this value, this much is the difference. So total error is this is square plus this is square plus this is square. That error is called the loss function here. So mean squared error, right? Or something else. And the second one is called regularization. What does it mean? So people find that when people are building the models have this tendency to start overfitting the data. Okay. So, like for example, if your data is like this, okay, if your data is like this, okay, so these are your data points, okay, so you have first equation that, okay, so this is my first equation. The second equation is this, and third equation is, okay, third equation is, okay, so between this third one, first one, and second one, which one do you think is more suitable for your scenario? One, two, or three? So you have these data sets, this, these data sets, and there is a blue, black, and red. One, two, and three. Which one is most suitable to this? That's correct. So second one is. right? Now, the models, when they get too complex, they have this tendency or bad habit of, you know, memorizing everything. So what you usually do is, right? So as the model becomes more and more complex, the model starts to memorize everything, right? And as the model is basically starting to learn and is not having too many weights. So when the model is too simple, then also it's bad. When the model is too complex, then also it's bad. Correct? So 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 simple model and complex model. Okay? So complex model. Now, simple model also has too much of error in the data. Okay? And complex model also has too much error in unseen data, the data that it has not seen. Okay? So the the way it looks like is that this looks like this. Okay? So you can see, so if you have to draw it like this is how it looks like, right? So there is some place here, okay, where, okay, so our role is to find a model that is neither too simple nor too complex, okay, which gives the smallest possible error, right? This one, too simple model will also have a lot of error. Too complex model will also have a lot of error because it won't be able to fit in the unseen data sets. Okay, it may memorize, like this model could be memorizing lots of data points. But if you see, if one data point was, let's say here, and here, and here, these will have lots of error from this curvy data model, right? So coming back to the point is the whole machine learning is all about finding a good model, neither too simple nor too complex. Or you can say neither too biased, we also called it biased, and variance. Okay. Neither it should have like a lot of bias, nor it should have too much of variance. Variance is in a slight bit of change of value, the outcome is absolutely different. Like for example, from here to here, it kind of just we went left and then it kind of gave error. Now, so that's called bias. This is also called underfitting and overfitting. Okay, so the whole idea of a machine learning model training is to figure out a model which is neither too simple nor too complex. It is somewhere in between. Okay, so it's like this, right? So you always make two parts of objective function. One is the actual loss, and other is the loss, or you can say regularization term. Okay, this is usually we call it L1 or L2 regularization. Usually, what does it mean? It means that we are adding. So when we say L1, what we do is we add the theta 1 plus theta 2 plus theta 3. Okay, so the bigger these values get, the more penalty you get. Okay, so what we do is, in order to make sure that the model does not memorize everything, we give it a penalty on too many of these thetas. Okay, so the more thetas or the bigger values you have of theta, the more penalty you get. Okay, so you have two terms. One is called regularization error, and other is called the training error, or the, you know, this part. measures how this part measures how well your model is able to fit the data. This part measures how complex is your model. Okay, is this okay, everyone? Yes? Okay, all right. So the training loss, right? The loss on training data is generally written like this. You this means let's say loss function is your mean squared error, right? So what do you do here? Let's say this was your data set. This was one data point. This was another, right? So what you do? Y predicted and actual Y. The model is saying this is the predicted value, right? This is called Y predicted. And this is called Y actual, right? And yi means there are three instances. This is one instance, this is second instance, this is third instance. What we are doing, we are computing this error, we are computing this error, we're computing this error, and then summing it up. So here, this loss function could be anything, right? Here we could have, let's say, a this minus this whole square. That is called mean square error. In case of regression, that is the error. In case of the classification, the error is usually uh, you can multiply the two values, taking the log of one value, multiply with another. That's called the classification loss, and sometimes it's called logistic loss, or sometimes it's called cross entropy. Okay, so basically, this is the right. So these are the usually the loss functions. One loss function is just take the difference, square it. That's the error between predicted and actual. This is predicted, this is actual. So that's the squared loss. Logistic loss is take the log of probability and multiply by another value. Okay, so that's all. And here you might see like what's happening here. This is basically after we have applied the logistic loss. That's what we have. So we basically first pass the value through that logistic or logic, or you can say softmax, not softmax, that's called sigmoid. Okay, this is sigmoid, and you pass it through that, and then you do the rest. Now, this is essentially what it is. Now, the regularization term, the second term in that equation, is usually either you take all the weights, square them, and then sum them, or you take the absolute value of each weight and sum them up. So that's called norm. And sometimes it's a combination of both of them. Sometimes it's a combination of ridge and lasso. We call that. Does anybody remember that name? So the loss function is sometimes the regularization term is sometimes is sum of the squares of all the weights, and sometimes this. Okay. So I hope this is clear. Y minus y predicted whole square and lambda times this one. Y minus y predicted whole square, lambda times this one. Right? This is called ridge loss. This is called lasso. Okay. And a combination of both of them, where we are saying, right, where we are saying y minus y predicted whole square plus lambda 1 w whole square plus lambda 2 absolute value of w's, right? That's called the elastic net. Okay. So you have a combination of both of them. So you can have different loss functions, different regularization term. Okay. Going back here. So again, overall objective that you're seeing here, it has got two parts to it. One is called the normal loss. Other is called, this is loss on the training data, mean squared error, and so on. This one is basically regularization loss. When your data is not trained, completely untrained, all the weights are, let's say, 0, right? What will happen? There will be too much of error here and too less error here. When the model becomes complex and these thetas becomes very big, okay, and they kind of absorb all the data, in that case, this error will be 0, but this error will be too high. Okay, this error will be too high, and hence, so basically there's a balance, right? Initially, this part is 0, all like small, and finally the second part becomes small, and first part become higher. So as we train the model, the loss goes down, and as the model becomes more and more complex, the as the model becomes more and more complex, the regularization term increases. So, and we want the objective function, which is sum of both the things, to be smallest. Correct? All right. Right? In case of logistic regression, we'll convert the predicted value into the sigmoid, convert that into probability, take the log of it, multiply with y, and that's how it looks like. So this is what it looks like in logistic regression. Is this okay, everyone? Okay. All right. No, it's only Rohan. I'm seeing Rohan and Matthew. Anybody else? Saurabh is also okay. Kamel is okay. So far, Srinath is also okay. All right. So basically, the objective function, this is very common to every model, whether we have neural network, whether we have naive Bayes, or anything where there is a training. Okay. Okay. So, so yeah. Why do we want to contain two main component in objective? Okay. One is optimizing training loss, meaning that we are better fitting the data. Okay. So if the good training fit is equal, meaning that it's closer to the data distribution. Regularization means that it forces the thetas to be smaller, and hence the model to be simpler. Usually a straight line is simpler than the curve is simpler than cubic equation, and so on. Okay, so the more the regularization, the better, simpler is the model. Okay, simpler models usually have low variance and they are most stable when it comes to prediction. Okay, so you would want to have simpler models as well as good fit, as in it should be well trained. All right, now let's talk about a regression tree. Okay, we're going to focus more about regression tree. Regression tree is same as classification tree, right? Contains one score for each leaf value. Usually, what in case of regression tree, what do you do? Basically, compare the characteristics of example, and then you keep on going till the leaf where that particular example is matching, and then from that leaf you return the average value. Okay, from the leaf you return the average value. That's called the regression tree. Okay, so you have, let's say, input, age, gender, occupation. You have age, gender, occupation, and you basically, and this is your tree. So you'll go around here saying if age is less than 20, yes, then go this side. No, go to this side. And then here we are saying, right, whether somebody likes a computer game X or not. So we have this decision tree, check the age, and then return the prediction score from each leaf. Each leaf is having a prediction score. This one is having +2, this one is having -1, and they return from here. Okay. So if this is our tree, this is our well, there are two trees. This is tree one and tree two, right? This tree one checks the age, and second one, the tree two checks how frequently do they use a computer, right? And here we are checking whether the person has like whether a person would like a particular game. You check the age of the person, and based on the age, this one is saying that the prediction as per the left tree is 2. This is how much is the chance that this person will use or play a particular game. Okay. And then the second tree is saying the chance is zero point 0.9. So what do? You add the two numbers, 2 plus zero point 0.9. So probability of this person playing a computer game is equal to the value given by the first one plus value given by the second one, right? Similarly, for this person, the age is 20. Yes. Answer is -1. Age is right. Does the person uses the computer? No. This person does not use the computer daily. No. And therefore, the answer is minus zero point 0.9. Minus zero point 0.9, -1 plus minus zero point 0.9, it's 1.9. Got it, everyone? So this is how a tree looks like. This is how a regression tree looks like. So you take the average value from all of them and then you basically sum it up. Or you can say that you take an average of the value. Okay, you basically sum up the values. Let's just stay there. Is everybody okay with this? Yes, these trees are created from same data set, but they are this one has one split based on the age. This one has split based on some other feature called whether the person uses computer daily or not. Make sense, everyone? All right. Okay. So by combining multiple trees, you can get better prediction, and that's called tree ensemble. Okay, so gradient boosted trees, random forest, all of these trees. So you can combine multiple trees, or you can take the data set and basically one tree based on some other features, other tree based on the other features, or a combination of the two. You can create multiple trees and then you combine these trees to have a better outcome. Okay, so every competition on the internet has been won by using the ensemble method. Tree ensemble means we have multiple trees created from the data, and you ask each tree the outcome. Okay, so you can think of it this way: that if you have multiple models and you ask multiple models about the probability of the outcome, and you take the average of the all, you get the best result. Okay, so all the competitions on internet are won by using the ensemble method. Ensemble method is nothing but you basically have group of models and you pass the instance through each of them, and whatever is the outcome you aggregate it. Okay, that's called ensemble. So in case of trees, you don't need to you, no need to scale or normalize the inputs. Okay, it captures the complex feature interactions and so on. It is scalable and used in real world systems. Okay, now we can do the ensemble on top of the trees as well, right? If you have, let's say, the K trees, capital K trees, okay, what do? You ask the first tree, they tell me what's the outcome. Then you ask the second tree, what's the outcome? And third tree and fourth tree, up to all the trees, we ask all the trees, what's the outcome? And then do the summation. Okay, so you have k number of trees. K number of trees have been prepared by someone. You are passing, asking each tree, what's the outcome for x1? And once everyone has given the outcome of x1, you take the average or you sum up all of these values. Okay, that's how you get the best outcome. Make sense, everyone? Yes. For the ith example, this is ith example. We are asking the first tree, what's the outcome? Then we are asking the second tree, what's the outcome? And then we are summing it up. Okay. So you can say that we are saying f1 of xi plus f2 of xi plus f3 of xi. So these are the trees, the first tree, second tree, third tree, like that. You have, let's say, k trees. Okay. So you are asking each of them what's the outcome, and then you are summing it all. Okay. That's called the ensemble method. Of course, it's going to be sort of average. Okay. But it's okay to assume that it's summation from all of the predictions. Okay. Perfect. So the parameter of the tree include the structure of each tree and the score in the leaf, right? A tree is basically structure means the decision boundaries, right? Like here in this case of tree, the tree one is having the first decision boundary as a is less than 20. This one is having use computers daily, yes or no. That's the decision boundary. So decision boundaries, the tree is nothing but group of decision boundaries, right? Decision boundaries within decision boundaries and so on. You can say, or you can say split like that. Right now, this tree has only one split. Other tree also has only one split. But in real life, these splits will be many. Okay. I hope this makes sense to everyone. So basically, 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 the tree is nothing but splits, and the parameters of a tree is the parameters on the basis of which we have done the split. Those are called parameters. And the the parameters, along with the parameters, they score in each leaf, because when you reach the leaf, that's when the tree returns a value. Okay. So when we say tree means two sets of things. Number one, various kinds of boundary conditions or the splits, plus the scores in the leaf. Okay. So we can simply say, we can simply use the tree like a function, f1, f2 up to fk. So when we say f1, f2, f3 up to k, this is essentially the functions. The tree is basically represented like a function. Okay. Okay. So instead of the usual regression, what do we have? We have these tree. We are learning the functions, meaning the splits and the values of the leaf in a tree. Okay. Instead of learning the weights, we are trying to figure out on what column and what value do we split each of the node, and also what value should we keep in the leaf. Okay. All right. Now, how do we usually learn the function? How do we usually learn these thetas, or you can say parameters? Okay, we define the objective and then minimize the objective loss. Okay, we minimize the objective function. Objective function has two parts: the training loss and regularization. The total of the two we basically can optimize or minimize. Okay. So in case of linear regression or logistic regression, you can use things like gradient descent, where we try to increase each theta and we keep on moving. In case of a tree, there is no straight method. Okay. The method is you pick up a column, pick up a value of the column, divide the data based on that, do the split based on that, and then check, did we did we do a good job or bad job? Okay. And that's what we do. We iterate over all of them and so on. Okay. Like, for example, if we want to predict whether I like romantic music at a time t or not, okay. So what I would do is, okay, I have, let's say, a data. So I split it t less than this value. Yes. Again, I split it t less than this value and so on, right? So basically here, if you see the time, time is one on this line. So first I split the data based on this here, right? And then here and so on. So this is the part where I met my girlfriend. Then here, right? Then after a while, there was, you know, the period where I loved the songs, and then again introduced. All right. So basically, you see on this line, these two lines, this line and this line. Okay. These two lines are called split. We split the data based on this line and this line. And then the average value on each side is called the leaves. Okay, we split the data, we again split the data. In one side, this is the leaf, then this. Right? So you have one here, another here, here. So this is how the tree looks like. Okay, so essentially the we have the output, whether I love the song or not. That's my Y. Okay. And this is the time X, which is the timeline. So first I split the data here, then here, and this is the value in the leaves. Okay, there are three leaves, one, two, three. These are the three values. And there are two boundaries, one boundary for this, one boundary for this. Okay. So I hope that tree is clear to everyone. The tree is clear. Okay. All right. Right. So these things are called split positions, and these things are the height of each of this thing is called the cell values. So how many total parameters? One, two, three, one, two. Correct? The splits are primarily the parameters. These values are basically in the leaf. Okay. So so basically what we need to learn is these heights of this is the predicted values. These are the predicted values for each of the leaf splits. Okay. The objective for single variable regression tree, okay, is, right, training loss, how will the function fit the data point, okay, and regularizations. Okay. So if we just split this too many times, okay, if we split it too many times, okay, we keep on splitting it too many times, right? What will happen? It will become much more, how should I say, it will just absorb all the data and will do the memorization. Okay. If we split it just too many times, for each instance we have the split, then it may not work because it won't be able to do the approximations. Okay. And even if it does the approximation, it'll do a very weird approximation. Okay. So if we split the tree too many times, the complexity of the function increases. Okay. If we do not split the it too many times, our loss will be higher because it will have too much of error. Okay. So So the objective for single variable regression tree is there's a tree loss. How will the function fit the data points? Regularization loss. How do we define the complexity function? Like, how do we define the complexity function? How many splits do we have? And second, the average or L2 norm or the height of each segment. Okay, meaning square of the difference between that. So that's essentially what it is, right? Okay, so if we do the too many of splits of this data, right? You have too many splits of the data, the the model is becoming more and more complex, and hence the ohm or sigma, what do you call this? All right, that is very, very high. The regularization loss is going to be very high because the model has become too complex. Okay, right? This is a wrong split. If we split at a wrong place, then also the the loss is higher because that's not a right place to split. Okay, this is a good balance. It has a good balance. This is basically the loss is correct. Okay, here the loss function, the actual training loss was wrong. Here training loss is correct. Here, here too many splits, though training loss was split at correct place. So training loss was low, training loss was low, but because regularization loss is very high. Okay. So overfitting, overfitting and underfitting. Okay. And this is the right amount of fitting. Okay. Now here there's not only underfitting, the model is absolutely untrained. The model is not trained properly, and therefore it's kind of underfitting. It's untrained model. Okay. Now, in case of the trees, specifically, what is XGBoost? XGBoost is going to be essentially like random forest, whereby you have too many trees or you have k number of trees and you combine all of them to get the outcome, right? So in case of the ensemble, what do? We ask each tree, give me the outcome, then we take the average of it, or you can say we basically sum up the values. Okay? We sum up all the values. Okay. So in case of the ensemble trees, you have instances where we are going over all the instances, computing all the loss, right? That's our loss, going over all the instances, comparing the predicted versus actual, and computing the difference between them and summing up all of them. That's called the training loss. The complexity of the trees is how many total trees do we have or total leaves do we have. We go over all of that, go over all of that, and basically for each tree you have k number of trees. You basically compute the total number of splits in each tree. You compute the total number of splits in each tree. Okay, and then you basically sum up all of that. So total number of splits and other regularization terms for each of the trees counted. So your objective function is loss function over training data and the the regularization term over all the trees. If you have k number of trees, you have k such things. Okay. Now, how can you define the regularization term? Right? One is number of nodes, which is basically how many splits did we have. Second is the L2 norm of leaf weights, meaning the total value of the weights in the leaf. When you talk about decision trees, it's usually heuristics. Okay, what do? You split the data based on information gain. Okay, what do? You basically, you go over the data set. You go over the data set, checking, should I split here? 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 Should I split at age less than 10, age less than 12, A is less than 13, A is less than 20, like that. You basically keep on trying to split and see after splitting, did we get good or did we go bad? Okay, that's called information gain. So you have the loss function, you compute before the split, after the split, check whether it went well or it became worse. Okay. The other way is that you create the tree, you come back and try to evaluate again, and that's called pruning the tree. Okay. The other is there are a couple of heuristics, right? If you know that till what depth do you can go, that will also help us in training the model. Okay. Next is the smooth leaf values. Smooth leaf values is in the values in a leaf are if they are equal or nearby. So those can be your criterias to basically train the tree. Okay. So most of these heuristics, most of these approximations, right, map well to the objectives, right? Take the formal objective view, right? Taking the formal objective view, let us know what we are learning, right? These objectives basically tell us a lot, right? The information gain whenever we are splitting is usually improving the training loss. When we are pruning as in eliminating or deleting some of the splits, that's called pruning. Okay, that's essentially improve the regularization term. Why? Because we are removing some of the splits. Maximum depth, okay, it's a constraint. When we are training a decision tree, we have a constraint on the max depth. We say that don't go below this depth. Okay, that way we can stop it from memorizing everything. If it just splits the data on every value in the data set, basically it will memorize all of the data. That's why one of the knob that we keep for training the decision trees is by having a control on max depth. Okay. The other is keeping the regularization on leaf weights. If the leaf weights are too high, then you get a penalty. If the leaf weight is too low, then you get a penalty. So, I mean, sorry, the more the leaf's weight you have, the more penalty you have. That's called L2 regularization or leaf weights. That's how you control the the overfitting versus underfitting in a traditional or a usual decision tree. Okay. Regression trees ensemble defines how you make your prediction score. It can be used for classification, it can be used for regression, it can be used for ranking, and much more. Okay. And it all depends on how you define the objective function. Okay. So far, again, recap. So we can use the squared loss in case of regression. In case of classification, we can use the logistic loss. Okay. And the bias variance trade-off is everywhere. We want the predicted or the functions to be simpler rather than too complex, right? This defines what we want to learn, objective and the model, right? So basically, based on the objective, we want to learn the model, which is simple, and it should not be memorizing everything, and we want to learn based on a certain loss. Okay. The question is, how do we learn it? Okay. Question is, can we can we use methods such as gradient descent? Okay. Can we do that? Let's say we have the split. We let's say we take a column in the data, we take a value, and we slightly increase that split, and then observe, is it going good or bad? Is it going good or bad? It's not really going to help. Okay. In case of the um, decision trees. Okay. So instead, because these are trees, not really numerical vectors. Okay, numerical vectors, because there is no way you can, right, slowly increase and go to the next value, because there is no way you can get to the boundaries. Boundaries are discrete values rather than continuous values. Therefore, you cannot use gradient descent to train a decision tree. Okay. Now, but the question is, how do we train the tree, or how do we find that model called tree, or how do we find that split based on which we can figure this out? Okay. Okay. A simple additive training, or we call that boosting, start from constant prediction, add a new tree or new function every time. Okay. So what do? Initially, you have no tree. At that point of time, the predicted value is 0. Okay. Then what do? You add one split. Okay. In that case, your 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 the outcome is whatever the first one did the prediction. Okay. And okay, you whatever first you did the prediction. Now the next one. Okay, like that. So you keep on, right? So you keep on adding these splits, or you can say you can keep on adding new functions, and you keep on adding these trees, and the accuracy keeps on improving, right? So the prediction at the y uh, t time, when we added the tth tree, this is the prediction. Okay, and this was the prediction at t minus 1 plus the prediction done by the last tree. So we had t minus 1 trees, they did this prediction this much. Now we added the tth tree, they give you the next prediction. Are you seeing that? So if we have 0 trees, no outcome, right? We had got 2 trees, the outcome from the first one and second one, we got one more tree, whatever, right? Whatever the previous one predicted, we are adding one more prediction to it, and like that. So as we keep on adding trees, the accuracy of prediction is increasing, right? Is everybody okay? We are basically adding one tree at a time. Okay? We are adding max depth means number of splits. That's correct. Okay? All right. So, it's an easier way to think about this is that basically we are adding one tree at a time. We added one, initially there was no tree, so nothing. Then we got one tree, then we got two trees, then we got three trees. So on addition of new function or new tree, your accuracy is improving. Everyone okay till now? Okay. This is fairly technical, so I'm guessing that most of the people will drop out. Okay, so yes, but I'll try my best to keep it extremely simple. This is a fairly advanced topic. This class is going to be more like a research level class. Okay. Yes, thank you, Prince. It means average of all trees. Yes. Okay. Right? So, or you can say the predicted value is sort of a summation of all. Okay, so you can just think of it that way. Okay, so though it says everywhere it's a summation, it's essentially average. Okay, because the predicted value, we have to take an average of all. Okay, all right. Now, question is, how do we decide that we need to add one more learning function or one more tree? Okay, now, basically, the way we decide is we optimize the objective. Okay, we optimize the objective, right? Remember the objective? Objective was loss function and number of trees. Okay, now we are basically changing that. That predicted value at time t is equal to predicted value of time t minus 1 plus the last value that was predicted. Okay, so here what's happening is that at time t, when we added the time t, just before that, this was the prediction, then we added this, and then this was the regularization term. Everyone okay? So every time what we are doing is we have an objective function, we add one more tree, we added one more tree, just one more tree. What happened there was, what happened there was, because of adding one more tree, the regularization term will increase, correct? Because we added one more tree, we added one more split. When we add one more split or one more tree, what happened? It has a more tendency to memorize, correct? And therefore, the regularization loss increases because it has more tendency to memorize now. At the same time, because of adding a new tree, because of adding a new tree, your loss will reduce because new tree will give some amount of predictions. Okay, so by adding a new tree, either you could go good or go bad. Why? Because on one hand, by adding a new tree, definitely your loss will go down. But at the same time, your complexity has gone up, and therefore it might increase your overall loss. It might increase the overfitting. As we are adding trees, model becoming more and more complex, and it is becoming more and more overfitting, memorizing, or you can say the function is becoming complex, and therefore it has a higher chance or higher freedom to memorize. Okay, so right, if we were, lucky enough to just keep adding the trees indefinitely, we'll keep adding the trees indefinitely. But initially, when we have no tree, then also we don't have any model. It is not going to give great results. When we have too many trees, then also it's a problem. So we need somewhere in midway, not at the end. Okay, neither too few trees nor too many trees, or neither too few splits nor too many splits. Okay, that's what we want to do. So here we are basically representing our loss function like that. This is the actual value, this is the predicted value. How much is the predicted value? Previously predicted plus predicted by the last tree that we have added. Here we are saying loss function of all the trees. Okay, in this sigma we are replacing with this. Okay, this sign. So we have computed this regularization term per tree, and we basically just putting that. All right, now now okay, right here I'll come back to this one. So here when you open this bracket, you would get something like this. Okay, so a square of second one twice of this times this plus y minus y dash whole square. Okay, that particular thing, and so on. All right. So right. So basically, so overall goal, your overall goal is to minimize this value. Your overall goal is to minimize this, the loss and the regularization term. Loss between predicted in the last round, which is basically last round plus one more tree. Okay. Yes. Is the constant same in both cases, like after adding a new tree? Yes, we are saying the constant is same in both. Okay. We can eliminate that anyway. Okay. All right. So your objective function is the loss between predicted and actual plus the regularization term because of newly added tree. Okay. Now this may look like complicated, but you can just convert it to squared loss and it'll look pretty simple. Okay. Now here. Okay. So I'm going to take a digression. How many of you remember the Taylor expansion? Does anybody remember Taylor expansion? No? No? Yeah. So the Taylor expansion says that if you have x plus delta x of any function, you can write it like this. Okay? Sorry. You can write it like this. F of x plus delta x times f dash x plus delta x square by 2 times f double dash x. Okay. Now, what does it mean? What does it mean? That if your function, okay, like let's take a case of, let's say, polynomial. Okay. If your function is, let's say, polynomial, like that, right? So when you say dy by dx, what will it become? This will become 0. It'll become a1x plus a2x square, right? So sorry, twice of this, okay? Plus thrice a cube x square, right? At the same time, if you say y of 0, what will it become? Become a0, okay? Right? A0. Then when you put, let's say, dy by dx and you put x equal to 0, what will it become? It will become a1, like that, right? And so on. So when you put it back into this equation, so y of x is equal to y of 0 plus a1. A1 is dy by dx at 0 times x. So like that. So you can basically, by differentiating this whole polynomial, you can find the value of a1, a2, a3 in terms of dy by dx, and you put it back, and that's the derivation of Taylor series or Taylor function. You can just search for Taylor series. It's actually fun to do it. Okay. So essentially, okay, essentially, it is a interesting thing that you basically your function looks like this. Okay, so you can actually generate the equations for sin x, cos x, and so on using this simple formula. Okay, simple formula. So take a look at the Taylor series. In simple words, right? In simple words, this part that you see here is what we are trying to do. So the Taylor series is f of x plus delta x is approximately equal to f of x plus first derivative of f of x and delta x plus 1 by 2 f of x like second derivative times delta x square. Okay. Is this okay for everyone? Yeah, we usually do this. Why we use Taylor expansion? We usually do this to find the equation or a model given the derivatives. If you know the differentiations, but you don't know the equation of something, you can use Taylor expansion. For example, you want to find out the expression, what does it mean by log x? Okay, does it mean by log x? Right? We know the we don't know the full formula of log x, though we know the differentiation of log x. Correct? So log x expansion, right? So using the Taylor series, using the Taylor series, right? You can expand sine x to this, cos x to this, e to the power x to this, log x to this. Okay? So that's basically what the Taylor series has been used for deriving the the functions, for finding the underlying functions. And that's what we are also doing right now. So we have this Taylor series. Now let's pay attention here. What if this is our x and this is our delta x? How would this look like? Right? For simplicity, we can also say that rate of change of loss L with respect to our yt minus 1, and similarly this hi is the second derivative. So we said g is our first derivative, h is our second derivative, x is this, delta x is this thing, okay, this thing. Now the equation looks like this. Okay, the equation looks like this here. So loss of, so if you put it in this, f of x is what? L. This is our L, right? Our function is L. So L of yt minus 1 plus g is the first derivative, g times delta x. Delta x is nothing but f of t. Okay, and then half of h and f square. So essentially we took this equation, this is our x, so this is our x, this is our delta x, right? And we did the expansion of this using the Taylor series. So we are saying loss of the next step is equal to loss before we added the before we added the last tree plus the first derivative of last tree times this plus half of the second derivative times square of the last tree value. Okay, so we basically did an expansion of this. So objective looks a little more complex now. Okay, the objective looks a little more complex now, right? Now you can make it look little simpler. Okay, if our loss function was, let's say, square term. If loss function was like a square term, what will happen? We take the derivative of this one, this becomes twice of this, and h, so g becomes twice of this value, and h becomes the derivative of this one, which is 2. Okay, so I hope this is making sense. If our loss function is yi minus yt square, if that's a square, so when you differentiate this, that becomes twice of that value, and h becomes the differentiation of this, which is 2. So your gi is this, hi is this, and you put back into this formula. This is how it looks like. Okay, this is how it looks like. It becomes super simple. So loss function y by t plus twice of this value times ft plus here 2 by 2 times ft square. So this is pretty simple now. Okay, not that simple, but still simple. Anyway, if you just keep all the constant aside, right, for a moment, this is how it looks like. Your function is looking like this. Okay, so this part is looking like this. Okay, so Okay, so basically, this is like we are just keeping it, uh, we are basically simplifying it further. So this part looks like this, right? Now, why we are trying to do so much effort to derive this objective function? Why don't just we do a hit and trial and so on? Instead of number of trees being the hyperparameter, if we don't know how many trees we can train, or should we go ahead and train a new tree, okay, we want to figure out should we go ahead or should how to optimally derive it. If we have like formula and we have the things in place, we can just immediately guess it rather than immediately get the answer rather than iterating over it. That's what we are trying to do. Okay, all right, like quick question to all, let's say y equal to x square minus 2x. Okay, what is the minimum value of y? What is the minimum value of y? Are you sure? It can be negative. Why can y be negative? Okay. So what is the minimum value of y? So for x equal to 0, y is going to be 0. Okay. X equal to 1, how much is y? That's coming to minus 1, right? 1 minus 2x. For x equal to 2, y equal to 0 again, and so on, right? All right. So my question to all of you is that is there a better way to do it? We want to find the minimum value of y. This is MIN, minimum value of y. Okay. Or let's say I have also put in like 3x square minus 880x. What is the minimum value of y? Okay. All right. If you want to find a minimum value of an objective function, what do you do? What do you do? What do you do? Go ahead. If you have to find the minimum value, what would you do? Okay. So let's see. Okay. One of the techniques is that you plot the graph. Okay. You plot the graph. Okay. And then you figure out the minimum value, right? You just iterate over it. But that's not really a good answer, correct? That's not really good answer. So you can do that. But there's a very interesting part. The interesting part is the gradient at the minima as well as maxima is horizontal, right? The rate of change of y with respect to x is horizontal, which means dy by dx equals to 0. And we know the formula. This is 2x minus 2, and therefore x equal to 1. right? On the similar line, if our y was, let's say, x square minus 20x, okay, plus 30, okay? Let's say this is your equation, okay? Now, how would you find the minimum value of y? How much is dy by dx? 2x minus 20, make it 0. So x equals to 10. And when you put that back here, so the minimum value of y is 10 square minus 200 plus 30. Okay. And that is how much? Minus 70. Correct? So minus 70 is a minimum value that comes at x equal to 10. Yes? So if we have an objective function, one thing we can do is we can differentiate that objective function and equate it to 0 and figure out what is the minimum value. Okay? Yes? All right. Let me give you another example. So y equals to x square minus 8x plus 9. What is the minimum value of y? Who can help me? Let's say dy by dx equals to dy by dx equals to 2x minus 8 equal to 0, x equal to 4. Thank you, Kamla and Prince. And when you put this back in this, how much is it? Y equal to 4 square minus 32. Is that right? No. Oh, plus 9. Sorry. You're right. Plus 9. Thank you, Prince. Yes? All right. Perfect. Perfect. So given an expression, you can find out the minimum value, right? By differentiating and equating it to 0 and then putting that value back. Okay. All right. All right. Let's go back and try to understand, right? What exactly is the tree? So we define the tree by a vector of scores in the leaves. Okay. So what do we do in a tree? Okay. We feed in our data. This one here we check. Is age less than 15? Yes. Is this male? No. We come here, say, okay, the weight is equal to how much? 0.1. So we return 0.1. We come here, let's for another instance, let's say for a boy, for a small boy, right? We check, is it age is less than 15? Yes. Is it male? Yes. We return this value. Okay, plus 2. If age is, let's say, if it's an elder person, age is 50, more than 15, okay, no matter whether it's a but whoever it is, we are returning -1. So these are the scores. So when we have the tree prepared, we can feed in an instance and it gives the value. We call this function an instance, it gives the value, right? So we define a tree by a list of scores in the leaves. Okay, the leaves are the outcome in our tree, and a leaf index mapping function that maps an instance to the leaf. Okay, so a tree would return the weights in the leaf at the end of day. Correct? The tree will give an output which is in the leaf. And which one will it give? The one that maps to the structure, right? The one whose characteristics are matching this structure, right? So I hope this is clear. So tree is a function in which we feed x. X is the characteristics of the input, and it returns the corresponding the leaf value. It returns the corresponding leaf value to the x. Yes? Everybody okay with the tree? All right. Okay. Now, right? Now, what we are saying is the complexity of a tree, okay? The complexity of a tree is how many splits does it have? How many splits does it have? Or how many, let's say, leaf does it have? One, two, and three. Total number of leaves are three. Okay, this T is basically number of leaves. Now, right? And then basically number of leaves times some constant plus weight square of these values, 2 square plus 0.1 square minus 1. So that, right? So here what you see is that given a tree, we can calculate its complexity like this, right? The square of all the value of leaves plus plus how many leaves does it have? Make sense, everyone? So given a tree, we can take the sum of squares of the weights, and that way we can calculate this, and we can also count all the leaves. That becomes our complexity. Okay. So, all right. Now, the overall objective of our function, if you go back to where we were earlier, okay, right? So we reached to this objective, right? We reached to this objective function that the first derivative after we did the Taylor expansion, we got to this place and so on, right? And we basically are saying that we will feed in the instance here. We will calculate the rate of change of loss for each of the instance, and we will basically feed into this and we'll get the overall error, right? Now here is a very important part. So your objective function is this. After doing the Taylor expansion, we reach here. Now the next step is we turn this complexity function into number of leaves and the square of the weights, right? That we did. Now, the next thing we do is instead of here, if you pay attention here, what we are trying to do, we compute the loss with respect to first instance, second instance, third instance, fourth instance, and sum up all that loss together. That's what we are doing here. Okay. But we can, like if you have t number of trees, we had t number of trees, what we can do is we can say that sum up this value for each tree. This is what we are saying. Do this for each tree. Compute this value and this value for each tree, and then we add it. Now, since we did this, this part went inside. So we have the summation of the GI and summation of H plus lambda and this. Now, okay, let's pay attention to this particular thing once we have rearranged it. Now, look at this. If we have a function f, okay, which is gx plus half of hx square, okay, at what value will f be minimum? So we say df by dx, we say g plus hx equal to 0, x comes out to be minus g by h, right? And when we put minus g by x back here, okay, here it'll be minus g times g by h, plus h by 2 g square by h square. The h gets cancelled. Okay. And hence we get 1 by 2 g square by h. Okay. So if we have a function like this, gx plus half of hx square, and we want to find out the minimum value of this one, what is that? This minimum value is at this. Okay, so the one that we wrote earlier, if the sigma thing, if we put it like g, and if this whole bracket, we write it like h plus lambda, this will turn out to be how much? G square by h, g square by h plus lambda. This at this value minus g by h plus lambda, we will have the smallest value of this. And how much will be the smallest value? We'll say g square by h plus lambda, right? So this whole equation has been simplified and optimized. Okay, so what we are trying to do is we are trying to figure out an optimal objective function which will be the minimum, and we are doing that minimization right away, right away, as in rather than doing the iteration again and again, again and again, doing the iteration, here we are doing the prediction using the calculus. We figured out this is the minimum value of the objective function and so on. Now this is the most important part of the XGBoost. XGBoost figured out that there is a better objective function, a smaller objective function, if we have the weight to be, to be something like this. Okay, so it says that if the the weights, the leaf values are equal to this factor, we would have the most optimum objective function. Okay, as simple as this. So instead of giving it all possible permutations, keep on trying all possible permutations, we optimize this objective function. So after all of the hard work, we found an objective function which is much more optimum, and we can just focus on this new objective function, and we basically just go over that. Okay, so what do? We have the instances. We calculate the gradient statistics, right? The G1, H1 for all of them, the first gradient, second gradient of the loss. And once we have that, what do? This is our tree. This is our tree. For this particular node, we have instance 1. This particular node, we have instance 4. This particular node, we have 3 instances, 2, 3, and 4. Okay. For this particular node, we have got G1 and H1. These two values, the rate of change of loss of error with respect to each value. Similarly, loss of error with respect to this value, loss of error with respect to this. So once we have that, what do? We calculate, we go start from the top, split the objective function. Did it improve? Did it become worse? Then again we split, we check whether it became better or worse, and that's it. So essentially, essentially, this has become right. This is this objective function is the one that is used in XGBoost. This objective function is what defines XGBoost. Okay, so the objective function is, very optimized. So this is our objective function, right? After all the calculation, right? What do? So now the method is you basically enumerate, like you go over the trees, right? You go over the trees, you start splitting, calculate the score, this objective function's score. Okay, and then basically find the best tree structure and use the optimal leaf weight. Okay, so essentially you take this objective function, we know that this is the optimum leaf weight. Okay, and basically Basically, with this leaf weight, there can be infinitely possible tree structures. So what you can do is you start at the top. Okay. Okay. So usually what people usually do is they grow the tree greedily, meaning they try splitting, they try splitting. If it is not improving, they stop. That's called greedily. Okay. So in practice, what people do is they grow the tree greedily. They start from depth zero, and then what they do is they split the leaf, okay, and calculate the objective function before and after the split. Okay. Before the split, this was the loss. After the split, this is the loss. The difference of the two is called the information gain. Notice that it was negative. Now the negative has become the positive. So this, right? This was, previous. We subtract minus this. So this is the information gain that we are having. This is the information gain, the opposite of the objective function. Opposite of the objective function is called the information gain. And the information gain is this. The right? You take the score of left child, score of right child, and then subtract the score before splitting. Now, this will tell us, as we are about to split, this will tell us whether to split or not split. Okay, this will tell us whether to split or not split. So you check the gain. Is there an advantage in splitting? Because as you split a node, as you split a node, find a boundary to split, and as you split, on one hand, your error will go down, but on another hand, the regularization will go up. Correct? The regularization loss will go up. Therefore, at every point of time, you try to split in a way that you do not make a loss. Okay, that's what you do, and that's one way to find. Okay, so what you do is, what's the gain at a split x equal x less than a less than here, and then you go to another value and then check whether that makes sense or not, and so on. Okay, so that's our algorithm for finding the split. For each node, we enumerate over all features. For each feature, sort the instances by feature value, use a linear scan, go from left to right. So you sort the data by feature value, split on one, split on second, split on third, and so on. That's how you do it. Take the best split along the features and so on. Now, what's the time complexity of the tree? So first for every feature, you do the sort, which is n log n. And then, and then once you have done that, you basically go over every value and try checking. So if you have D features, you're going to repeat this process D number of times, and we have to go for like K label or something. So this is what is the complexity. It can be further optimized by doing the approximation, sorting, caching the sorted features, and so on. But can we scale to very large data set? Yes, yes, we can scale. It can be scaled for a very large data set by splitting. A very important question that people would ask you, that can the XGBoost be scaled? Yes, the answer is yes. The way people do is they split the data set into parts and create different trees, and then train those different trees really fast and then get the results. Okay. All right. So yeah, let me go back. It's not batch gradient, but yeah, it's kind of batch training for trees. You that's called what do you call that? Patching or boosting. It's like that. So you basically split the data into parts, train some trees on one part, train some other trees on another part, and then use that. Okay. You can handle the categorical variables simply by just one hot encoding, and that's it. All right. Okay. The other way is that you train the tree and then you start unsplitting the things. Okay. So what you do is you basically create a tree first way. And once you finish creating tree, then you go up and undo the split. And how would you judge whether to undo the split or not? By again checking the same information again. Before and after the unsplitting, did did our objective function go better or worse? So this is another thing, that once you're done with training the entire tree, full tree, what do? You start again from the top, start not the bottom, from the top, start trying to unsplit some of them. Okay. And that, see how it goes. So this is something that people do, and this technique is called pruning. Pruning is undoing the split. Okay. Okay. Stop split if base split has negative gain, but maybe a split can further, you know, have the benefit. Maybe sometimes there is ungreedy approach. Sometimes what you think is that, okay, maybe right now, splitting is not giving advantage, but maybe in future they will give. So you just keep on moving and so on. Okay. So post pruning is growing a tree to a maximum depth and recursively prune all the leaf splits with negative gain. Okay, so that's essentially what it is. So boosted tree algorithm is add a new tree at each iteration. Beginning of the each iteration, we calculate the loss. Okay, we calculate the loss and the first derivative of the loss. Use this statistic to greedily grow a tree. Okay, greedily grow a tree, and this is our objective function. And okay, so if, right, add a new function to the model, if to the model, this one, usually instead of this, we do some epsilon instead of the whole thing. We just add a new tree with the epsilon set around zero point 0.1, and we do not do the full optimization at the each step, and so on. So essentially, we grow the tree gradually. Okay, so you can take home the assignment for everyone. A question from Prince is that, is XGBoost useful for online data? Yes. XGBoost is definitely better than every other uh, tree, whether random forest or gradient trees. XGBoost is definitely better than every other tree. Okay. All right. So this is the take-home assignment. You guys can take a screenshot. Okay. So how do we build a boosted tree classifier to do the weighted regression problem such that each instance have an important weight? Okay. And yes, so weighted regression problem, as in some are more important than others. If you have to do that, how would you build that? Second is, if let's take the example of the time series again. If you want to learn a step function over time, is there a way to learn the time splits other than the top-down split approach? Okay, think over it and okay. All right. All right. Go ahead with your questions, everyone. Yeah. So a question from Prince is that, can we do it? Can we? Yeah, this is an important question for everyone. Okay, let me rephrase the question. Imagine that you trained a model with a 1 billion records. Okay, you trained the model with 1 billion records. Tomorrow, say 10,000 records came in. 10,000 records came in. Will you train, do you need, do you train the whole model again, or what do you do? That's the question, right? Okay. A better technique is every day just train a probably, let's say 10,000 records you got, right? So what do? Take these 10,000 records, take some more sample, some more records from other buckets, and create a new tree. Create a new tree, retrain it. Okay. And then basically just discard some old tree, add new tree. Because if you do the XGBoost on whole data, what will happen is you will end up with you will end up with the whole data to be trained again, the whole model to be trained again, and that will take a lot of time. So therefore, you do not train again the entire model. Instead, you just train the model part by part. Okay, so that's why you cannot do the incremental training. Okay, was that your question, Prince? All right. A question from Matthew is, my first thought is to weight the tree by the leaf for objective. Yes, yes, that's good. That's good, Matthew. And yes, all right. All right. Wonderful. Wonderful to have all of you in this discussion. Any other questions at this point? Okay. Wonderful. Yes. This was a little bit more mathematical treatment of the tree. And yes, so with respect to certificate, somebody will send it to you. Don't worry. Okay, just drop a message to the team. A question from Rohan is, can XGBoost handle the data imbalance? Good question. Good question. It can handle, but again, uh, it it can handle the data imbalance, but again, there is a chance that the model will be, imagine that in one leaf there are only few records, in the other leaf there are more records. So yes, but it'll be able to handle the data imbalance better than other models. Okay, all right. And decision trees can do this thing really well for you. Okay, the the data imbalance problems. Okay. Usually, let's say you are trying to identify whether there is an anomaly detection or so, you can use the trees or decision tree or random forest or gradient boosted to identify the anomalies, or not only anomalies. For anomaly you need the unsupervised learning, but here I'm talking about, let's say you have some classes which have uh, less less number of labels, so in that case it can. A question from Prince is, what is the best, Keras model or XGBoost? Keras models or you can say neural network has overtaken everything. Okay. Okay. All right. Okay. Thank you. Thank you, Matthew. All right. So yeah. Okay. Um, all right, Prince. So yes. So see, neural network models that are part of TensorFlow or Keras, they're actually much better than XGBoost now, specifically when you have data and when you are handling things like images or and so on. You can basically just have this. But the reason why I wanted to have this XGBoost session today is that the the way the decision trees are derived, there is a value in that. Okay. If you think about it, say tomorrow you learn, let's say, neural networks, right? In neural networks, as we grow the deep neural network, like you add the layers, on one hand, we are improving the accuracy. On the other hand, we are increasing the loss due to overfitting, right? And basically, we need to have the balance between the two. So the similar philosophy, similar maths that we do today could be applicable there. So this XGBoost session, the purpose was to give you a feel or an overview of how the entire mathematical formulation work, just so that you can visualize the overfitting and underfitting in terms of a mathematical equation. Okay, so that was the core idea of this discussion. It had couple of very interesting ideas in it. Okay, all right, wonderful. Thank you, everyone. Have a good day. All right. Okay, so have a good day.